So this is the second question we are going to discuss. Here, two particles are moving in a horizontal plane. Earlier, we discussed all the motions in vertical plane. Therefore, this is a different type of problem given under SHM. Let's start. Two particles A and B, each of mass m, are connected on either side of an inelastic string. Inelastic. This is inelastic. Lying on a smooth horizontal table. Particle capital A is connected to a point O on the table using an elastic string of length L. There are two strings. One is inelastic, normal strings, what you have learned under mechanics in physics, and the other one is elastic, length L and modulus of elasticity mg. Both strings are placed perpendicularly to table edge. Perpendicularly to table edge, and part of inelastic string fixed to B is hanging vertically downwards. Now it is clear. Particle M connected or particle B is hanging vertically down from the table. Particle A is on the table. And also particle A is connected to a point O using an elastic string. All these string parts are perpendicular to the table edge. That means if I view this from top, if this is the table, this is the top view, the string is like this. String connected to particle A, again A connected to a different point A. This is particle A. Then this string moves down. But we can't use this top view for our calculation. We have to draw it like this, a side view. This is particle B hanging down, weight mg, tension, let we take it as T1 because there are two types of strings with two different tensions. This is particle A having the same tension because this is the same string. A is again connected to a point O from an elastic string. That is a different type. Therefore, there is a different tension, T2. So this is the arrangement. There is a table like this. This is the table surface. Don't think about this edge. Somehow this string is falling down. They have not given there is a pulley or anything is not given like that. No need to consider. This is the arrangement. The particle B, I'm reading here, particle B is kept at O and released from rest. This should be A. It's a printing mistake. This should be particle A, not B. The particle A is kept at O. This is taken to O and going to release. And particle A is not going to reach this edge in its resulting motion. Now can you identify its motion? When A is taken here and released, what will happen? Because of this drag, given by particle B, A will move towards the edge. But that is until the natural length of this elastic string is reached. The natural length of the elastic string is L. Until OA becomes L, A and B will move as one unit. It will move down as one unit because these two are connected from an inelastic string which is not going to extend. Because of that reason, both A and B will move down. B will move down, A to left hand side as one system. But when A reaches the natural length of this elastic string, now the elastic string is going to extend. Okay, you have to think like that, otherwise you can't solve this problem. That is the most important thing here. You have to consider A and B with this inelastic string as one system. Okay, now I'm going to apply F equals MA to both A and B separately in order to find their acceleration, because we don't know the acceleration of particle B which is moving down. You can't take it as gravitational acceleration because it is connected with A. It is connected with A. If it is just connected to a ceiling and release, it will move without the effect of a different particle, without the effect of the string. But here B is moving with A, so there is an effect given by particle A for this downward motion of B. Therefore we have to calculate its acceleration or the system acceleration separately by applying F equals MA to A and B separately. First I am going to apply F equals MA to B downwards. Mg minus T1 is M acceleration. We don't know. It is not x double dot because I have not marked an x extension up to now. So I have to consider the acceleration. I took it as simple f. This is my first equation. Now F equals MA to left hand side to particle A. What are the forces acting at A? T1 minus T2. T1 minus T2. Mf, because both of them are one system, therefore they have the same acceleration. Now I can add these two. Then T1 get cancelled. I am having Mg minus T2 equal 2Mf. Mf plus Mf become 2Mf. Now what is this T? I have made a mistake here. I have made a big mistake here. There is no T2 still in this problem. Why? We are considering this motion before the natural length of elastic string is reached, before reaching the natural length. Therefore, this string is in a slacked form like this. Therefore, there is no tension. It is still slacked. Therefore, there is no T2 term here. Cut it. There is no T2. Then I can add 1 and 2. T1. Only T1 tension is there. They get cancelled. Now I can cancel m in both sides. My f is g over 2. G over 2. Why didn't we take T2? Still, this elastic string is not stretched. It is not applying a tension. That's why. Okay, after reaching the natural length of this elastic string, after that it will extend a tension. Now we know the acceleration of both A and B before reaching natural length. Now I can find the time taken by this particle A to reach natural length of this elastic string, because in Roman number 2 they ask in a time. For that I will take the time here itself. For that I have to apply S equals ut plus half at square to left hand side. This is applied for particle A. Then move distance is L, because we are considering now particle A is reaching the natural length of elastic string. Therefore, from here to here, the length should be L. There is no initial velocity, it is just released from rest. Half into what is the acceleration? G over 2 into time square. Then what is the time? 4L over G, square root of that. Then I can write it as 2 square root L over G also. So that is the time taken by this particle to move from O to A. Let me label that as TOA. Now we have to consider the velocity. The velocity of the particle. I'm going to draw it again. Now the particle A is going to start its simple harmonic motion. That's why I'm going to draw another diagram. Now this is stretched. Therefore it is applying a tension T2. Here T1. This is the natural length of the elastic string L. Now we have to find this velocity V. For that I have to apply V equals U plus AT, because I have time. V equals U plus AT in this direction for particle A, for this particle, from O to A, from O to A. There is no initial velocity. Acceleration was G over 2. Time, what is the time? 2 times square root L over G. Then 2 get cancelled. We can cancel G also. Here we have root G. Normal G is square root G into square root G. Then the simplification is square root GL. That is the velocity. After reaching point A, particle A will start its simple harmonic motion. Now I have to consider the general location of particle A like this, which is extended x distance. Now apply F equals ma for particle A to that direction. What are the forces? Here we have T1 force, T1 tension. So this is the same elastic string now which is extended up to this point. Therefore there is no T1 here. It is moved to this location. This T2 is here. Then the forces are T1 minus T2 equal mx double dot equal mx double dot. X double dot is the new acceleration of particle A. Now it is moving under simple harmonic motion. Okay, I can write T2 because tension of an elastic spring is modulus of elasticity into extension divided by its natural length. We know modulus of elasticity. Is it given? Yeah, mg. Natural length is given, extension is x. But we can't find T1. T1 is the tension of the inelastic string. And we don't know that value. Therefore, I have to consider F equals NA to particle B also. Like in this case, where we found common acceleration. This is for particle B, it is moving down under mg minus T1 force. Now what is the acceleration? It should be the same acceleration. Why? Always particle A and B are moving as one system. Therefore, x double dot is the common acceleration in this case. This is my equation 3. This is equation 4. Now I can add 3 and 4. 3 plus 4. T1 get cancelled. Answer is mg minus T2 equal twice mx double dot. Now what is T2? T2 is the tension given by elastic string. We can apply our equation modulus of elasticity given in the question into extension x over natural length L. We can cancel m in all the terms. M not equals to 0. Now I have 2x double dot equal g minus gx over L. Divide both sides by 2, then you have g over 2 minus gx over 2L. In order to find the characteristic equation, you have to consider a negative term first and take g over 2L out. Then you have x minus L. Now our statement, this is in the form of characteristic equation of simple harmonic motion, where omega square is g over 2L, omega square is g over 2L, center x is L. You have to equate this bracket to 0 and subject x, you have the center of the simple harmonic motion, that is L. So this extension x should be L. Then you have the center of the simple harmonic motion. Let's mark that center somewhere here. This is the center C, which is L away from A. L away from A, starting point of this extension. Okay. Now we have to find the amplitude, because we have to identify the maximum distance moved by this particle along the table. That is the amplitude point. To find amplitude, we have to use this equation. We know the velocity v as root gl at this location, isn't it? We calculated this velocity for particle A when it reaches the natural length of the elastic spring, that means at A. So this is at point A. Velocity square will give you GL. Omega square is G over 2L. Amplitude square minus. Then what is the distance to this point A from the center of simple harmonic motion? From here to here, value is L. So x is L. X square becomes L square. 2L square equals amplitude square minus L square. Amplitude is square root 3L. Take minus L square here, it becomes 3L square. Amplitude is root 3L. That means this particle A will move another root 3L distance away from center, away from point C. This is the center. Amplitude is the distance, maximum distance moved by a particle away from its center. So that is root 3L. Now in the first Roman number, they are asking us to show the length from O to edge of the table is more than this. They gave us if particle A will not reach the edge, if this particle A not to reach this edge, this length of the table from O to A must be more than this. That means what is the distance from O to center of motion? Here L, here also L. That is altogether 2L. Then distance from C to maximum distance moved by the particle, which is the amplitude, is root 3L. Therefore, maximum distance traveled by this particle E from O will give you 2L plus root 3L. Distance traveled by the particle is root 3L plus 2L. Then take L out, you have 2 plus root 3. So this distance should be more than, this distance must be less than the length of the table. In other words, length from O to edge of the table must be more than this traveling distance. So you can write that statement and finish Roman number 1. Length from O to edge of the table is more than this. Then only particle A will not reach or will not fall from the edge of the table. Okay, so this is the answer for Roman number 1. Take screenshot. It's a little bit tough because we have to consider a horizontal motion. Now the second part. If particle A will not reach the edge of the table in its resulting motion, show that A will reach O again after this time. Motion is started at O. Particle A reached capital A point with an acceleration of g over 2 and taking this much of time. After that, it is performing a simple harmonic motion. So this is regarding that simple harmonic motion. Now we have to find the time taken by this particle to complete this simple harmonic motion, which is from A to this extreme point where we have our amplitude. Now I'm going to draw a simple harmonic motion again, like this, including all the information. Point O, O to A. This is the extreme point. We label that as D. Then somewhere here we have our center. We calculated that and marked it as C, which is again L distance from A. Then we calculated the amplitude. It was root 3L, that is from center to extreme point D. Now from here to here, particle is performing a simple harmonic motion. This is the amplitude point, extreme point. Now I have to construct my arc like this from extreme point. And we have to connect this arc with finishing point of the simple harmonic motion in opposite side, which is D. And also have to connect center and this point like this. Now this part is similar to previous questions we discussed, same thing. This is the angle covered under simple harmonic motion. Now there, in this expression, we have tan inverse. That means I have to select my theta such that when I apply tan for that theta, I have this answer. I can get this answer, tan inverse root 2. And also the angle given is pi minus tan inverse. Therefore, this angle to become pi minus tan inverse, I have to mark my theta here, isn't it? Think this total angle is 180. If I mark this small angle as theta, this covered angle becomes pi minus theta. Now what are the known things, known sides in this right angle triangle? This is L, this is same amplitude, therefore it is root 3L. So tan is, since we want tan, I have to calculate this one because tan is opposite side divided by adjacent. We can't consider root 3L, which is the hypotenuse. Then from Pythagoras we can find this is root 2L. Square, take the square of hypotenuse, take the square of this side, subtract these two, which will give you 2L, 2L square. Take the square root, is root 2L. Then what is your tan theta? Opposite side divided by adjacent side. Therefore theta is tan inverse, L will get cancelled, root 2. Then time of particle A moving under simple harmonic motion is equivalent to angle it covered divided by its angular velocity. Angle is 180 minus theta over omega, that is 180 minus tan inverse root 2 over omega will become 1 over root 2. What is our omega? Here is our omega. Here we have, it is square root of this fraction. Then when I take the reciprocal, it will be 2L over G square root. Reciprocal 2L over G. We have to take the square root. Do we have this part? Yeah. Here we go. Root 2L over G. Pi minus tan inverse. There are some additional things as well. Now what is the total time? Total time is TOA plus TAD. Total time is TOA plus TAD. O to A taken time is this, 2 square root L over G. 2 square root L over G plus What is TAD? This is the time. 2L over G square root 5 minus tan inverse square root 2. This is from O to D. Then here they are asking the time taken for A to reach O again. That means it is going to come back to this point, covering the same path. That means we have to take 2 times. We have to multiply this again by 2. Okay, here they have taken 2L over G 2 times 2L over G square root out as the common factor. Then from this, I can take 2 out. I can take this 2 out. Then here we have L over G. By force, I have taken a square root 2. A square root 2. But in the first term, we didn't have a square root 2. To cancel that, I have to take 1 over square root 2. Plus, here we had square root 2L over G. So we have 5 minus tan inverse square root 2. But this side, we had another 2. Therefore, I have to multiply each and every term by 2. Without doing that, I can do the simplification like this. See, I can write this 2 here. This 2 is written here. And I have taken square root 2L over G out. But this 2 is still in the numerator. I didn't take this 2. I took this 2 out for the common factor. And to cancel this square root 2, which I took by force, which was not there in this term, I wrote it in denominator. Now I can cancel these 2 and get my answer. 2 divided by root 2 is root 2. This is the total time.